The title of this chapter is Spectroscopy, and we're going to deal in particular with nuclear magnetic resonance spectroscopy, otherwise known as NMR. It is a technique that's been around for about 50 years, and compared to every other way you can analyze and identify organic compounds, this is by far the most useful. It can tell you a lot about how the atoms are put together in organic compounds, allows you to easily distinguish things like alcohols versus ethers versus esters versus aldehydes. It's easy to determine what class of compound you have, but also it gives a lot of detail about how the atoms are connected. So we're going to deal a little bit with the theory behind how it works and then see some examples. Well, the nuclear in the name nuclear magnetic resonance refers to what's going on in the nucleus of atoms, and in particular the nucleus of the hydrogen atom that is essentially just a proton. So a lot of what we will see corresponds to proton NMR because the nucleus we're interested in is just the one that has just that particle. The magnetic comes in because it involves using very strong magnets, and we'll talk a little bit about what that resonance idea has to do with. In this picture from the text, on the left you've got protons with their positive charge, and they're depicted as spinning in one direction or another. Particles like that can have this property called spin, and when you have a spinning particle that's charged, it creates a tiny little magnetic field. And so the pink arrows are relating the direction in which that magnetic field is oriented. Maybe the North Pole at the arrow tip and the South Pole at the other end, if you compare it to little bar magnets, for example. And on the left, those would be randomly oriented in a sample unless you expose that sample to another magnetic field, a much stronger external field. And on the right-hand side, that's what you're seeing over here. So we have these quite giant magnets that are sometimes used to analyze these tiniest of particles. And when you bring these protons close to a magnetic field, they kind of snap into place, either to be said as parallel to that external field represented by the big green arrow here, or else alternatively they are said to be anti-parallel or oriented opposite. You can see 3 of the pink arrows are pointing up, those are aligned with the field, and then the 2 pointing down. And so you get some of both orientations, but the purpose of the magnet is to force the orientation to be one or the other. And what happens next is that if you apply some energy in the form of radio waves to these protons that are already aligned by the field, you can cause some of the ones that are anti-parallel to be to switch their orientation. We say they flip their spins to become aligned with the field. And it does require radiation in the radio frequency area, so it's very common to radio frequencies you use to pick up stations in your car radio. So it's not a very strong energy we're talking about. But if you have just the right frequency for a given magnetic field strength, you can cause that spin to flip. And that's really what resonance is all about, finding just that perfect radio frequency that will cause that to happen. Now in NMR you can have different instruments that operate around different frequencies. 200 megahertz, 200 million hertz is common, and a lot of the results you see in chapter 13 from this experiment, they're referred to as being obtained on a 200 megahertz instrument. So it involves again a big magnet, but also something that can generate those radio waves in that area. And we tend to compare every organic compound and its behavior to the one shown here. TMS, or tetramethylsilane, is our standard, and it's the hydrogens in these methyl groups that are doing the resonating. So if you have a 200 megahertz instrument at a certain strength of magnetic field, you can cause the hydrogens in TMS to flip their spins or to resonate. And when you compare how that works for TMS versus other molecules will have a slightly different radio frequency that will cause them to resonate if you're comparing it to what TMS does. And so we compare molecules to that, and it turns out that the slight differences in the amount of radio frequency needed to cause a spin to flip depends entirely on the chemical environment of those protons, whether they're part of a methyl group, whether they're attached to oxygens or other elements. That has a big effect on just what type of radio frequency is used. So we'll talk a little bit more about how NMR operates and see some examples of it in the next video.